Class, we're going to go over lecture 9 now. And at the end of the last lecture, lecture 8, I talked about the test coming up and just double checked what was on it, and it will cover lectures 1 through 11. Okay, so these lectures will be posted on beforehand, kind of like they all have been. I'm trying to stay about a week ahead. So there is potential to kind of move ahead a little bit, maybe give you a little bit of time to study for the test. If you do the lectures exactly when they're scheduled, you'll still learn all the material before the test, but you may not have as much time to study it before the test actually begins. So just look at the schedule and keep that in mind as you start to prepare for the first exam that's coming up. Okay. All right, let's get into lecture 9 here. All right, so this one we're going to be talking about a little bit more about radioactive decay, talking about half-lives and also different applications of radioactivity in our life and where we sometimes might see radioactive decay. So just to start, as a review from the last lecture, go ahead and try to balance the nuclear equation here. All right, let's go ahead and solve this. So again, on these equations, what we're really trying to do is just to first balance the number of protons on the left and on the right, and then also balance the number or the atomic mass on the left and on the right as well. Okay, so we have on the left side we have 92 protons in uranium and then 0 protons here on this neutron. So we need a total of 92 protons on the right side. Okay, so 38 plus 54 would be 92, right? So we don't need to add any more extra protons here. So right away we could choose D, I guess. Well, let's keep going with this. So if we balance the mass units, we have 235 plus 1, we have 236 on the left side, okay? And then 90 plus 143, okay, so these two together, we would have, what is that, 233, right? So that means we need 3 mass units up here. Now there isn't really anything that has 3 neutrons and 0 protons, okay? But we could just say that we have 1 neutron that looks like this, and then we need 3 of those in order to make this equation balanced. So that might be something else that you might run into as you work through these problems. The reason it wouldn't be any lithium or helium is because those contain protons, right? So those wouldn't work. Awesome, okay. Okay, and then just for fun, I'm not really expecting anyone to get this right, but go ahead and try and do this question. All right, so I'll go ahead and answer this, see what everyone guessed. Usually we do this in class and we can kind of watch as people answer, and it's kind of interesting to see what people think gives the most ionizing radiation. And banana phone is the answer. Kind of silly. I mean, it just says phone because there's some other phones on there. But obviously, bananas can't make phone calls. Anyway, all right. So really this is just a banana. Okay, so like cell phones, you've probably heard emit radiation, and some people say they can cause cancer. Different radios can emit radiation as well. And this is ionizing radiation, which we'll talk about. But bananas actually contain radioactive potassium in them. And don't worry, this isn't like anything that can hurt you or anything. As we'll see in the PowerPoint, is that pretty much everything gives off ionizing radiation, okay? So, yeah, you don't need to cut back on your potassium or your banana diet here. So ionizing radiation has enough energy to knock an electron out of an atom or a molecule. So we talked about ions, which are atoms that either have more or less electrons in them. We've talked about that. So ionizing radiation is a radiation source that hits an atom and knocks the electron out. And because of that, creates an ion. And this is the mechanism for biological damage when your body receives radiation that's harmful to you, okay? So a Geiger counter, the way it works is has argon gas inside. And when it's exposed to a radiation source, right, it starts clicking a lot. That clicking is measuring how many argon ions there are present. So if there's no radiation, then it would just be argon. There'd be no ions. But as the radiation source hits the argon, it ejects an electron, okay, and makes this positively charged argon that registers on some kind of meter and gives the clicking that you would hear with a Geiger counter. So the more clicks, obviously, the more radiation that you have going on. So ionizing radiation, there's a whole spectrum, right, of different waves here that we're exposed to. But the ones that really we're worried about ionizing radiation is with UV, right? The sun, we know can cause issues. X-rays and gamma rays. And then also the ones that we've talked about before, alpha, beta, and positron emission. Those all shoot out particles that can then cause ionizing radiation. So an alpha particle that shoots out of the nucleus of another atom could hit another atom and cause an electron to leave, which would cause ionizing radiation, okay? All right. So we're going to talk a little bit about the strength of the different radiation particles that we talked about, right? So alpha particle, if you look at these, it has a very short travel distance, okay? Only 2 to 4 centimeters. And it can be shielded really easily with just clothing or paper, okay? This is how far it would penetrate into your tissue if it hit that. And you kind of see this diagram on the left showing that alpha radiation really doesn't do anything to us, okay, from the outside of the body. Beta can penetrate a little bit more deeply and cause issues in skin and tissue, right? And alpha can cause issues on the skin. But really organs could only be affected by gamma rays, which are much smaller. So you can see the distance here. You have 200 to 300 centimeters and then up to 500 meters for gamma rays. Okay, and they could penetrate through, or sorry, to shield them, you would need lead or thick concrete in order to shield from gamma rays. And beta particles, heavy clothing, gloves, lab coats, stuff like that. Okay. So alpha particles are the least dangerous source, like I said, of external radiation. And the reason I say external is because if something was ingested, right, if you ate something that contained an element that underwent alpha radiation, now that it's inside your body, it could do a lot more damage, right? I kind of think of these as like maybe some analogies that make better sense to you, but for me, I think of alpha particles as like shotgun. Right? Shotguns don't travel very far necessarily, but they can do a lot of damage up close. Beta particles, I would think of as like a 22 or something, right? Still not super long range rifle, but it could do damage a little further. And then gamma rays would be, you know, like a sniper rifle or something. It could do a lot of damage from really far. And, but anyway, I don't know if that makes sense or not, but that's kind of my way of thinking about it. So we talk here about if you ingest or inhale alpha emitters, it can be a lot more dangerous because alpha particles have the most mass. Okay, so they can do a lot more damage than beta or gamma if they're inside your body. And a lot of this is just kind of some fun information to think about. and just kind of understand the general principles here. I may ask questions like, which these particles would do the most damage from an external radiation source or something. And that would be gamma rays, right? Or I could say which would be the most damaging if ingested, which would be alpha particles. Stuff like that. You don't need to know exactly like how far an alpha particle travels or anything like that, but just kind of understanding the relationship between the three would be important. Okay, so we're going to talk about a few units here, and it's kind of funny, kind of confusing, I guess, but there's 3 different units basically. Well, there's 6 units, but each measurement has 2 units. One is like the common unit and another one's the metric unit and stuff like that. So you may have to convert between those, but I would give you the conversions when that needs to happen. Okay, but for this, I'll just run through these real quick, pull everything up, it's a little easier to see. So this first one here, CI and BQ, right, refers to Curie or becquerel. Okay, and then the Curie is the common unit, and the scientific unit is the becquerel. And then this would be the conversion between the two, which I'd give you if you were asked to do it. Okay, and this really talks about the activity of a radiation source. So like a Geiger counter, the more frequent the clicks are on a Geiger counter, the more Curie, right, that measurement would go up. So it's saying how many disintegrations occur per second is the unit. So you can think about it as like how many clicks on a Geiger counter per second or something like that. A rad or gray, okay, are used when you're discussing exposure. So if your body is exposed to something, how much of the energy was absorbed by your body, okay? And then REMS and sieverts are discussing risk. So what happens here is you take the gray, so again, the gray is talking about like how much energy came off of the radiation source. And then it's going to be multiplied by a certain factor depending on what kind of radiation it is. Okay, so let's say you receive 1 gray of beta radiation, okay? It's just 1 sievert of radiation. And the reason is that these aren't, there isn't much mass, right, for any of these. And so the damage they can do is pretty minimal. For a neutron or proton, they have a little bit more mass. So they do 10, you'd multiply the grays by a factor of 10 to see how many sieverts you've received. And then for alpha, since it's such a big bulky thing, right, if it's ingested, you would multiply it by 20. If it's not ingested, it doesn't really do anything to the inside of your body, right? So anyway, this is just a factor that's going to take about the amount of energy given off by a certain radiation source and multiply it by a factor to say how much damage can we really expect from this radiation source, okay? And when we're talking about how much radiation something gives off, it's generally reported in sieverts because that's really what people care about, right? How much damage it's doing to our body when we receive the radiation. Okay, so just a quick little quiz, kind of for fun. We're going to see which one of these do you think gives off the highest amount of radiation annually, okay? So we'll go through these. So food, different sources of food, like I said, bananas have potassium, which is a radiation source. So different foods going to have different radiation sources. And that's 0.4 millisieverts per year, okay? These units may not have much importance to you. Later we'll talk about like how many sieverts we are okay to receive per year. And then it kind of gives you a better idea of what this really means. But 0.4 millisieverts per year. 2-hour flight is only 0.04 millisieverts per year. So 2-hour flight gives off that much. Concrete and brick walls contain radiation. And then weapon tests fallout. So This would be like, I don't know, the army or someone testing a nuclear weapon, and the radiation that would be spread right after that is very minimal to populated areas. Okay. All right. So let's talk about what our annual dose is of radiation. Okay. So it kind of depends on where you live. So if you're at sea level, you're protected a little bit more from the UV. So you only receive 2.6 millisieverts per year, right? This is total of everything you'd receive per year if you lived at sea level from the cosmic radiation. And then from the ground, okay, so you also have radiation coming out from the ground, and those are some numbers there to show you how much you receive per year. So you might think that we're getting a lot of radiation from like all these things. So we're about, Utah is really, we're looking at these two numbers, right? We get more radiation from the sun and from the ground living in Utah. Some of you may not be in Utah right now, so good for you. Anyway, you'll see that this really isn't a big deal. If you add in the food, it's another 0.4, right? You add in airplane flight, it's another 0.05 millisieverts. This really shows us, gives you a better idea, I think, of how much radiation something gives off, right? And how much you are okay to have as a radiation. So if we look at the left, so sleeping next to somebody gives off 0.05 microsieverts, okay? And if we go down here, like an airplane flight gives out 40 microsieverts, okay? And then this is showing that all these put together is about the same as the 3 of these little blocks, okay? So let's say you live in a stone or brick or concrete building for a whole year, you're going to get about this much radiation, okay? Anyway, you can look through this. It's kind of interesting. Mammograms here, a head CT scan. This is your yearly background dose, okay? So kind of just what everybody gets. It's about that, 4 millisieverts. And then this is your maximum yearly dose permitted for a US worker, 50 millisieverts, okay? So you can see out of all these, we don't even come close to getting the maximum allowed for a US worker. And even the maximum allowed for a US worker isn't even enough to do anything. So on this next slide, we'll talk about that a little bit more. Okay. So again, like we talked about, there's about 50 millisieverts is like how much a worker would be allowed to receive. And this is really only monitored at a place that has the chance to receive high levels of radiation. But less than 250, there's really no detectable response, okay? So we're pretty safe. Once you get above that, you start to see issues. So at 1 sievert, so 1,000 millisieverts, you start to see your white blood cell count dropping. Greater than that, you'll start to see radiation sickness. And you go up from here, we have 5 sieverts, is the LD50, which is the, we'll talk about it on the next slide, but lethal dosage that would kill about 50% of people. And then greater than 6 sieverts, pretty much anybody would die within weeks. Okay, so LD50, again, these are amounts. Different organisms are less susceptible to radiation. So bacteria and insects can handle much more radiation than humans can handle. Right, again, so 5 sieverts of radiation would kill 50% of the people, of humans, right? Okay. Okay, so that's a lot of information, just kind of interesting. Mainly you want to know the units. You want to know that alpha particles are the most damaging if they're ingested compared to beta, compared to gamma, stuff like that. So most of the questions on a test that would come from this lecture, a lot of them would be related to half-life. So the half-life of anything is the time for the radiation level to decrease to 1/2 of the original value. Okay, so for example here, at this beginning point, you have 40 to 0, 40 radioactive atoms and 0 atoms of product, whatever it's decaying into. Okay, and after about 1 half-life, this is these units are just half-lives. So after 1 half-life, you'd be 20/20, right? 40 of these, or sorry, 20 of these 40 would turn into 20 atoms of product. So you lose about half of it. And then you do another half after 1 half-life. So if you have 20 radioactive atoms, you now have 10, right? And then after another one, you have 5. Then you'd have 2.5, right? Then you'd have 1.25. Then you'd have 0.0625, okay? So every half-life is just going, the radioactive atoms are decaying by 1/2, okay? Cool. So that's the idea of half-lives there. Okay. You might have heard of like carbon dating, and it relates to this principle as well. So you might have wondered, how do they know how old a bone is, or how do they know how old a tree is, or something like that, right? If an archaeologist finds it. So carbon-14 has a half-life of 5,700 years. So if you look at like an analysis of a bone, you could see what percentage of the carbon in that bone is carbon-14 and what percentage is carbon-12, which is the product of the radioactive decay of carbon-14, okay? So if you look at the bone, if you look at an old bone of a human or something, and you see that it has carbon-14 that is about 25% of what you absorb in a normal person right now that's living, you could make the assumption, you could figure out how old the bone is, okay? So 25% is a quarter, right? So it's half times a half, so that's 2 half-lives. So if you know that the half-life of carbon-14 is 5,700 years, you could multiply this number by 2, and you'd get about 11,000 years. So you know that the bone is about 11,000 years old at that point, okay? Cool. So let's do the carbon dating. So go ahead and pause the video real quick and try and answer this quiz question. All right, let's go through it. So we have calcium-47 is used to measure bone metabolism. Has a half-life of 4.5 days. The hospital receives a sample containing 88.0 milligrams of calcium-47. How much is left after 18 days? Okay. So we're starting with 88.0 milligrams, right, of this calcium-47. So how much is left after 18 days? And 1 half-life is 4.5 days, okay? So after 4.5 days, we should have half of what we started with, right? Calcium-47 is the radioactive isotope here. So we would go down to 44.0 milligrams, okay? So we're starting with this, so that's not the answer. After 4.5 days, we have 44.0. Okay, if we do another half-life, that's another 4.5 days, right? That would get us down to 22.0 milligrams, okay? This would be a total of 9 days after both of these. Okay, another 4.5 days gets us down to 11.0 milligrams, right? Total, we now have 13.5 days. And then if I do another 4.5 days, we would have 5.50 milligrams, right? And then this would be a total of 18 days here, okay? So after 18 days, we have 5.5 milligrams, which would be E, okay? Okay, sorry, here's all the stuff underneath. Cool. So hopefully that makes sense. Half-life is just the time it takes to lose half of whatever you started with. Okay. Okay, here's another little quiz question to practice this principle. So if you have, or I guess go ahead and pause it. Try this out first. Okay, so I'll go through this. If the amount of radioactive iodine, 123, used to treat thyroid cancer in a sample decreases from 1.6 milligrams to 0.4 milligrams in 39.6 hours, what is the half-life of iodine? Okay, so we know our starting, which is 1.6, and we know we're ending with 0.4, right? So it says, what's the half-life? Well, in order to know the half-life, we really need to know the total time and how many half-lives occurred during that time, or how many half-lives occurred during that time, right? So half of 1.6 would be 0.8 milligrams. So that's one half-life, right? And then half of 0.8 is 0.4, which is what we end with. So that's one half-life. So in total, we went through 2 half-lives to get from 1.6 milligrams down to 0.4 milligrams. And 2 half-lives took 39.6 hours. So one half-life would just be half of 39.6, right? So it'd be 29.8, I believe. Okay, 29.8 hours would be the half-life of iodine, 123. Okay. There are some like equations you might be able to look up. Those are generally more useful when the question asks for something like if this question said it decreased from 1.6 milligrams down to like 0.3 milligrams. In that case, it's hard to calculate the half-life easily because it's not like on the questions that we've seen, right? It's exactly one half-life every time, or 2 half-lives, or 3 half-lives. The questions I will ask, you'll be able to answer just thinking through like this. You don't really need an equation to do it, so don't worry about that. But anyway, that's kind of the general idea there for half-lives. I think that's it for that lecture. So go ahead and keep studying that and work on that in the homework. And as always, let me or Promoda, our TA, know if you have any questions, and we're happy to answer them. All right, we'll chat with you later.